We started to see some of the benefits of lazy programming and some of the challenges when we worked with it in Haskell, which is by default lazy. Um, and so it would be nice to explore some of the same concepts in Python. So let's ask ourselves first, is Python a lazy language? Well, if we look at arguments to functions, here we have some function f of x that does nothing. If I pass it as an argument, time.sleep1, it has to evaluate that argument before it can call f. So it's not lazy on arguments the way that Haskell could be, where we could pass in an argument and that argument didn't actually have to be evaluated until it was used. For example, here this argument is never used. So why should it be evaluated? Well, in Python, arguments for functions aren't lazy. So that's one way in which it's not a lazy language. It's eager or strict. List members, maybe we could put things into a list and they don't need to get evaluated until we pull them out of the list or we build a new list from that list, for example. Well, it's not lazy in that regard either. If I put time.sleep1 as an entry in a list, it will sleep before it builds that list. If I put that into a list multiple times, it will sleep multiple times. This also means if we had some hefty calculation at each index in our list, well, all of the sum of those different hefty calculations runtime will be required before my list even exists as an object in Python. So we don't get those friendly, lazy lists like we did in Haskell, where we could just define something to be a very large or expensive or even infinite list, and it just waits to evaluate until we ask for item number 50 from that list or something. Python's going to generate the whole list and do whatever might need to be done to evaluate each item in that list as well before or at the time that the list is created. Now, how about logical statements? If I say false and time.sleep1, time.sleep1 equals none, then we do actually get that short-circuiting brand of laziness that we talked about back when we were discussing in Haskell. So I already gave away the answer to this back when we first talked about laziness. No, Python is not by default a lazy language, but it does have some bits of lazy evaluation built into it in the form, for instance, of the logical operators, where we don't have to evaluate the stuff on the right-hand side before we evaluate the left if the left already gives us our answer. False and anything is false, so I don't need to do the right-hand side. So there are little bits that are automatically built in like that, and we're going to look at some ways that you could do lazy programming or lazy evaluation in Python by choice as well. One way that we could introduce laziness is to hide some evaluation behind a function. We know that the bodies of functions don't get evaluated until that function is actually called. So here, for instance, I could build that list where the sleeps don't actually get done until I'm pulling items out of the list by creating a lambda function, which is an anonymous function you may remember from our earlier discussions. Or I could even create a full-fledged function using def. Either is just fine. But if I create a function whose body is time.sleep1 or the square root of some very large number or whatever other evaluation might take up time that we want to be lazy about, I can do that. And then I put that function in as each entry into my list. The only trouble with this is that the items in the list, as they come out, are not the value that we wanted. So if instead of sleep, this was the 5,000th Fibonacci number or something like that, then what I get out is not the 5,000th Fibonacci number. What I get out is a function that could generate me the 5,000th Fibonacci number. And so then I have to actually call it to evaluate whatever was lazily stored there. So I can use functions to kind of hide evaluation and save it. The only problem is that my list is going to contain functions, not the values. And so it will be up to me or up to my users to call the function that comes out of that list. That's not quite as user-friendly as, say, the Haskell lists, where they actually built up the evaluation in the form of a thunk and held on to it for us. And then they just give us the value when we ask for something from the list. So this is hinting at a way that we could do something like this in Python, because functions are objects, because they can easily be stored in a list or a map or a tree or whatever, then they can be used to do a sort of lazy evaluation. But it's a sort that's perhaps not the most user-friendly, because users don't want to have to call a function that they get out of a list. We could, though, generate a structure that allows us to generate an individual value and be ready to generate the list. Again, similar to how Haskell did this, where we got the next value and then we had some thunk or some delayed evaluation for how we would get the rest if we needed it. Well, this function actually sets us up to do that. It's a Fibonacci number function, and it doesn't, however, just return a single number. What it does is it returns a number that's been fully evaluated and a lambda function for generating the next number. So when I ask for something out of that structure, I'm going to get the first value, for instance, and the function for creating the rest of the values. So when I call fib, that's what I'll get out, is two things. The first Fibonacci number, 0, and the function for creating the rest of the Fibonacci numbers. And then I can use rest, which you'll see was just a variable. It's a variable that points to a function. So the second item in this tuple that's returned will always be a function. The first item will always be a value. So our users do get, in this case, the information they want. It's just that they also have to do a little juggling to hold on to the function that would generate the rest for them. This still is not the most user-friendly format. Most users, again, are just going to want the number. They don't want to have to hold on to a function that would give them the rest of the values, and for that function to change each time it's called. So rest actually is getting a new value each line here. As I call through, it's a new function to generate the rest from then on, and another new function to generate the rest from then on, and so on. This is not the most user-friendly way to go about this. So Python does provide us with a structure that is at least a bit more user-friendly than the tuple of value and function to get the next value or that sort of thing. It's set up in the form of what are called generators. And first I'm going to show you how you do it in your code, and then we'll talk about the idea of generators overall after we get a little bit of a feel for how we would do this in code. So the key to it in Python is the yield keyword, which is like a return, except we don't have to have every answer. We only have to have the current answer. if you think about, say, a sequence of values like the Fibonacci numbers. So I yield the current Fibonacci number, and then my code is going to resume at the line following that yield if someone asks for the next number, or the next number after that, or the next number after that. So here we've got that we do have to store a generator object. We'll call it fibs. It's the result of calling our Fibonacci function. So our Fibonacci function does not return a value in terms of a single Fibonacci number. It returns a generator that could give us Fibonacci numbers. So the first Fibonacci number we can get by saying next fibs. So we get the next from that generator fibs. And that would give us 0 the first time around because C is 0 in the first call to this. And then we see that N and C get modified when we call next fibs again, because the yield here the first time gave us the 0. And so that yield will return the 0, and the function will know to resume right after that yield when the user tries to get the second Fibonacci number. So then N is set to N plus C, and C is set to the previous value of N. This is a way in Python that we can do sort of variable swaps or updates where C gets N's current value and N gets some new value after that. So this is a shorthand for what you might have to do with like a temporary variable typically. So N and C get updated, and then our loop continues again, and we yield the new C. That would be 1 in this case because C got N's value. So it's 1. Then when they ask for the next Fibonacci number, the program resumes after that yield where C was 1 and N would be 1 as well. And so it will update C to be that 1. N will become 1 plus 1, so 2. And we'll loop back through and yield that second 1. Now we see that C would have gotten updated to 2 and would give us the 2 the next time we ask for the next fib. And we even can loop over generators. We do have to be careful because, of course, the Fibonacci generator here is an endless loop. So this looks like a very confusing piece of code to most people because that loop never ends. But what it's allowing us to do is just like our infinite lists in Haskell, a generator will generate us the next item, next item, next item for however long we care to ask it for values. But do be careful when putting a loop in place that uses a generator. It will work, but it may work forever if that generator has an infinite number of values that it can create. So here this would just keep printing Fibonacci numbers forever. We probably should put some sort of stop into it or something like that. And you'll notice this one will start at 0 because I've done a new call to fib, which creates us a new generator with C starting at 0 and N starting at 1. So we could also have 2 running sequences of Fibonacci numbers, for instance, or we can have multiple generators created from that same function, in other words. This one will keep advancing from where it stands, the fibs that we created there. If I asked for the next fibs and next and so on, it would keep advancing separate from what's going on in this loop here. We can also do yield and create generators for finite sequences as well. There's no problem with that, except that you have to be able to stop. Basically, if my function for a generator ever hits the end of its function, then I get a stop iteration error. So I create a generator by asking for tens 3. That 3 provides the maximum number of tens that I'll be able to generate with this generator. And so I can ask for next, next, next 3 times. I'll get 1, 10, 100. There's no problem with that. But when I try to ask for next again, I'll get a stop iteration error. So I do have to be careful that if it's a finite sequence, I don't let my program explode with this, and we'll look a little bit at that further in a second. So when the function hits the end, then the generator stops generating values. This is nice in for loops because it's what tells your for loop for a finite generator when to stop. So here I've said tens with a max of 5, so we can generate 5 powers of 10. And this one will just go 5 times. And then when the while loop ends and we reach the end of the function, then we will stop generating values in the for loop. And our for loop here will also be able to end. So generators are similar to iterators, except for the idea is usually they are calculating values to be given only when the value is requested. In other words, they are introducing lazy generation of values into our programs in Python. You cannot step back to past values like we could with our Haskell lists, where our lazy list would keep all of those past values. This has some good and some bad to it. It means that generators can be very memory efficient and possibly even very computationally efficient because you don't have to store the whole sequence of past values. Where in Haskell, as we generated the 10 millionth prime number, we had all of the previous prime numbers stored in a list that was getting very large by that point. If we don't need all of those earlier ones, then a generator can be useful. It lets us just keep our vision on where we are currently. If we know we're going to need to hold on to those past values, then it's best to save them in some other data structure after they're generated. So here, for instance, I've created a generator and I'm storing each one in a list that I'll be able to look back at later. It's also worth noting that there is a format in Python 3 for comprehensions with parentheses that create generators as well. So if what you were doing in here was an expensive operation and you didn't want to pay the cost of it all up front, then you do parentheses instead of brackets, and you've created a generator. So this is a generator for powers of 10, just like our tens function before. And this is only going to give us the first 3 values of 10. So we're able to ask for the next. If this was an infinite number or 3 million or something like that, then we could build up this list of known results so far if we thought we were going to need to reference them again. But some of the beauty of the generator is if I know I won't need those earlier powers of 10, let's say I was using them for looping, or I was using them to provide the user with some short-term temporary information, then I don't have to hold on to them all. They're not clogging up memory there. So in Python 3, when we do loops using range, as we've often seen, or if we just generate a range, that actually creates an object that's like a generator. It doesn't have quite the same interface, so we can't do next on it, for instance, but it will wait to generate the different values in that range, which again saves memory. If it's a very large range, we're not holding that whole list from 0 to 100, or 0 to 99 rather, in memory, or 0 to 5 million, or however large our range is. We're only holding a single number at a time. So the ranges that we loop over in Python 3, they are actually similar to a generator, creating their values as you go through the loop. You can turn it into a list by casting to a list if you needed the full set of all of those values. And we will then not be the same as the original range because, of course, it won't keep any sort of concept of where its current location is, and it will be the full memory version of all of those numbers in a list. But ranges that are equal to each other can be compared so that we can say, is the range that I'm going over today the same as the range that I went over yesterday, for instance? Be careful when switching between Python 2 and 3, because in Python 2, range actually makes a full list like we did here, and therefore can use up lots of memory. Xrange makes this generator-like object that we can iterate over. So if you want the benefits in Python 2 that we've talked about here, then you would want to use Xrange, especially for very large ranges. So we saw before that generators can cause this error, this stop iteration error, when the next is requested and they have no values left to generate, for instance, such as hitting the end of the function that the generator is based on. So what can we do about that? It would be nice if, like in Java for iterators, we had a hasNext kind of function that we could just call and see that there was going to be some next value. But we don't really have that. So there are a few ideas of things you can do to be clean and friendly with generators in Python. One of the things is, of course, to use the built-in systems that we know work well with generators already, like comprehensions or for loops, that we know the for loop will stop when the generator no longer has any values left. So why handhold and do all of this manually if we don't have to? Maybe we can just use a for loop, or we can just use a comprehension and use our generator that way. If for some reason you actually need to step item by item through the generator, then you can do your own sort of handling of when the generator runs out. The generator doesn't give you some default value to indicate that it's done because of the fact that there's no universal way to be sure that that default value won't come up as a real value somewhere in your generator. For instance, if your generator was generating numbers and it just gives you -1 as its result when it's run out of numbers, well, what if -1 is actually a valid result as well in your sequence? Say you were talking about, balances for bank accounts. Well, the negative balance can happen. You don't like it, but it can happen. And so similarly, if you give none as the default value when a generator has run out, it's also possible that none might be the correct value in your sequence somewhere, because there is no correct result, but there are still more steps that could be taken from there. For instance, if you were given a generator that provided you the maxes of various lists, if there was no max among that list, maybe none is a valid response for that. And so the programmers of Python did not build in any automatic giving of some end indicator value in generators. They raise the exception of stop iteration if you try to ask for the next value. And that doesn't have to be the end of the world. If you know something that could be a reasonable indicator that you're done and that there's nothing left in your generator, then you can write your own little helper function here that takes a single item and it calls next when it's possible, and when next causes an error, causes the stop iteration, it just returns you whatever end indicator makes sense for your sequence specifically. But you do have to explicitly select what your end indicator is going to be for whatever makes sense in your situation. So this is another of those cases where explicit is better than implicit. in Python, we would rather explicitly say we have stopped iteration, even though it's an error. You can handle that error, and you can just simply from that point forward know that you stopped iteration and that there's nothing left to get from that generator. And so this just illustrates another of those cases where to non-Python programmers, this kind of structure seems a little silly. Why can't I just check whether there's a next thing or stuff like that? But if you think in the Python paradigm, to explicitly say that you have stopped iteration fits this Python mentality and pushes you in the direction of those one obvious ways of doing things, like a for loop or a comprehension, to go through a generator rather than trying to sort of manually do it yourself and force a direction that doesn't really fit the structure of the language. So here we've seen that Python by default is definitely not a lazy evaluating programming language, but that there are approaches you can take, some functional type approaches where you define your own functions, and because functions are objects, we can store them in lists, we can return them as results, we can do lots of different things with them. These functional approaches probably won't be the most straightforward to the average user of your code, perhaps won't even be the most straightforward to you, a person who has done at least some functional programming already. And therefore, Python also has this system built in of generators in which we generate a single value as we step through. We can write functions that create generators by using the yield keyword, and these generators are able to plug in to many of the built-in systems that we've already seen in Python in terms of creating them by comprehensions, iterating over them using comprehensions, and for loops that go through them automatically and will stop if the generator reaches its end, and that they follow this Python philosophy of explicitly stating when iteration has stopped if you're trying to ask for the next item one by one.